welcome to the department seminar. Sorry, I was caught on the phone. If anyone is interested in flower blooming data, let me know. That's why I'm late, so I apologize for not being able to hang up the phone on this individual quicker. But I have to introduce Andrew Dzambo. Dzambo.
Close. Yeah.
Today. Andrew got his degree at Penn State, a bachelor's at Penn State, and then a master's at Oklahoma. And then came here a year and a half ago, right?
3 years.
3 years.
2016. You only know me for a year and a half, though.
2.5. Okay, that's why. And I've interacted off and on with Andrew. The one thing that has impressed me, or that he has impressed upon me, is he has a very diverse set of interests, and I think we're going to see some of that here today. He's also very active. I do have to acknowledge that he's the organizer of the Pi Day competition. I do have to bring that up. What's that?
Tweet that thing.
Who won that? What's the conflict of interest
You have
here?
to verify you have to also acknowledge your.
Oh yeah.
Who won that this year?
Who won that this year? Yeah, who did win that this year? Anyway, but he was the one, actually, I do have to, speaking of scientifically thinking, I do have to point out that he didn't have enough pies for the competition, and so he suggested that I make 2 pies and just disguise them, but use the exact same recipe so that we have a control against which to test the judging. So he's thinking scientifically even to that level. Today we're going to hear about a side project that he started looking at during one of his courses, and which has developed into something that he's interested in.
Sorry, was there a difference between how the pies were judged or not?
No.
There wasn't?
There were 2 pies that were exactly the same.
And
Did
were
they get the
judged
same-
similarly?
Just about, yeah.
They got the same score?
Almost the same score. They got the top 2, actually.
You can say it came full circle.
Yeah.
Literally.
2 pies.
2 pies on.
We had 2 pies.
Is that on YouTube right now? Is that?
It will be, yes. It's not streamed live, but it'll be on. Thank God.
All right. So anyhow, thank you, Dan. I appreciate that.
I don't know that the thanks are in order on this one.
Yeah, but they were delicious, and I do appreciate that. Yeah, it's always a good day when you eat pie. Anyhow, yeah, so, yeah, thank you all for coming out. This is, yeah, I guess a topic, that I've been very interested in, really, like, for, I guess, a long time on, I like clouds just in general, but I also like to know the role, I guess, of, like, how have things been changing, like, both historically and in the future here. So since this is kind of, I guess, a side project that I've kind of developed through a couple courses, some results, I guess, are borrowed from those courses, but if at any point you guys have comments, you want to interact a little bit, please don't hesitate to stop and discuss this, because I'm still learning a lot, I guess, about this topic here. So I'll begin here. And yeah, so this is from a couple days ago. So I'm thinking about, again, yeah, this role, like the role of mid-latitude cyclones and how it affects us with in a changing climate or so. Mid-latitude cyclones, I guess, you can generally see, all across the globe at a given time. So in any one given hemisphere, it's about, you'd see 6 or 7 of these features or so. Very, in I guess a satellite image like this, which is, full disk image here. We have our system that we had from a couple days ago. The center of the low pressure is all the way up, like north of Labrador, but it extends all the way down into the Gulf of Mexico here, and in the southern oceans here. We have one feature, I guess, that I noted here that goes from about the middle of the East South Pacific Ocean, pretty much almost all the way down to, maybe not all the way down per se, but down to Antarctica or so. What generally happens in our climate, most of us know this, is that there's an excess of energy that's generated at the tropics. It has to be transported poleward, and this energy transfer happens through these mid-latitude systems here, which you can follow pretty much with these giant cirrus shields, these paraclinic leaves, however you may want to think about that. So again, yeah, that's one of the key ideas there. The biggest key idea, I guess, that we have here, which is, I guess, point number 3 here, is that in our changing climate here, historically and thinking ahead, is that the strength and location of mid-latitude cyclones will change in some capacity in our changing climate. climate. And as I dug into this a little bit further, like there's actually pretty big differences what happens in both the northern and the southern hemisphere. And it'd be hard to go through this and not talk about some key motivations here. So if we know that at given locations, mid-latitude cyclones generally affect us during the fall and the spring seasons and whatever hemisphere you're at. If these systems, for example, move northward into locations that are generally devoid or don't experience these type of weather phenomena so often, they're going to be considerably more affected. Like we're well equipped, for example, to deal with, brutally cold temperatures during the winter time, high humidity events during the summer, the occasional flooding event too. But if we move northward or southward, into areas that don't necessarily experience these, think about Omaha, Nebraska recently, for example. That's a pretty considerable change that could be more of a prevalent thing in the future. So it's something worth thinking about too. Another thing that I've kind of found interesting too, at least from some recent papers I've read, is that the presence of storm tracks at forward altitudes can also affect sea ice extent. What type of feedback that is, still a little bit beyond my comfort zone, but still just kind of worth noting too, because we've noted over the last, especially 40 years, that sea ice has retreated dramatically, and there's been a large amount of warming in the Arctic. And finally, I guess a really important one too is that precipitation extremes at higher latitudes will become more common in a changing climate, especially if the current trend holds true. So I've introduced, I guess, a couple ideas here. We're talking about climate change, we're talking about mid-latitude cyclones. So there's a lot of things, I guess, that you can think about, or knowing my audience here, there's people here that are radiation experts, climate experts, mid-latitude experts. So we're going to walk through individual concepts one by one, and we'll start with Earth's energy imbalance here. So we generally know we get all of our heat from the sun, so we have some type of flux, I guess, that's downward on our atmosphere here, and in order for our climate to balance itself, we have to expel some of that heat in the form of outgoing long-wave radiation. So the net radiation, I guess, that we receive in our climate at a given location is, of course, the simple difference between what's coming in versus what's going out. And that difference, if, for example, if this difference is positive here, like for example, 2 watts per square meter or something like that, the only way for our climate to balance out is to warm our atmosphere, warm our surface, add energy to the reservoir, such as the ocean or our atmosphere here. So thinking about this more complete, I guess, or completing the picture here, this is fairly recent from Graham Stevens back in 2010. So he provided an updated energy balance figure here of just where does all the energy go like once we receive it here. So of course we see clouds, we know that some of it's lost to absorption in the atmosphere, there's clear sky interaction, some of it goes into the ocean, and then for the outgoing part of it, we generate sensible heat, latent heat that's received by the clouds re-emit both back into space and back towards the Earth's surface here. So as you can see, this gets pretty complicated pretty quick just from a radiation and a climate balance type standpoint here. So I guess a number worth pointing out too is that the top of the atmosphere balance is estimated to be about 0.6 watt per square meter with an uncertainty of 0.4. So it could be anywhere between 0.2 and 1 watts per square meter that are the Earth's net imbalances based on the most recent updated satellite observations and all the available observations and analyses that we have from our best models. So I'm going to discuss that a little bit more in a different type of framework here in a few slides. But I think when you think about that imbalance, where does all that energy go? Or how does this manifest itself in terms of a surface energy increase? So we know that the Earth is warmed by about 1.3 degrees Fahrenheit over the course of over the last century, actually. And when I think we explain to our family members, like, okay, the Earth is warm here, but for example, it might be colder here in one location, warmer here. You generally see across the globe that it has warmed mostly everywhere. There's some spots in the southern ocean here that have cooled by maybe a couple tenths of a degree Celsius or so. And there's a couple spots, I guess, in the northern ocean, so like the northern Atlantic Ocean and the northern Pacific Ocean, where there's been some slight cooling, but you probably can't help but notice the really big dark shades of red at the Arctic, or around the Arctic Circle, and some of those increases in surface temperature are upwards of 4, 5, 6 degrees Celsius actually. So a tremendous amount of warming over the last about 30 years or so, based on this specific record here, points to that our Arctic is warming extremely rapidly. And using some of the products that I'll have available for this talk, will show, I guess, kind of why that's the case. So just very interesting stuff to think about here. So this is just, again, surface temperature, which is related to the energy that's received by our climate system here. So now, let's talk about the role of mid-latitude cyclones in all of this. So I already said this once, but again, worth bearing again, that they are primarily responsible for the redistribution of heat, moisture, and momentum in our atmosphere. So the passage of these mid-latitude cyclones, so if you live in these mid-latitudes, they're accompanied with often heavy precipitation, strong winds, very dramatic temperature changes, like sometimes it could be 60 degrees ahead of the front, and then maybe 20 degrees behind that. So you're talking, pretty dramatic shifts in weather pretty quickly. If we're moving, again, if we're changing like where these happen, across the globe, more temperature contrast, higher precipitation, it's certainly something to, again, continue to consider as we think about climate change. And a lot of people, as you would expect, have kind of thought about this problem already. Like, there's a large number of methods that exist, to create climatologies, classify mid-latitude cyclones, track them, and ultimately see how they've changed historically and in the future. So I think one of the best ones, at least that I was able to read and understand, was by Ulrich. He did a review paper back in about a decade ago or so on just a classification scheme for mid-latitude cyclones. So on the top figure here, we have the northern hemisphere, and the bottom panel here is our southern hemisphere. So this is simply a contour figure showing the density of storm tracks that happen at this given, or in these locations here. And as some of us might have already figured, but in case we didn't already know, the highest density of storm tracks actually occurs like at fairly high latitudes actually. So in the winter case here in the northern hemisphere, and for the summer case on the right here, the biggest density of storm tracks in the winter is actually just south of Greenland and across the Black Sea, where they're seeing anywhere between 50 to 60 storm tracks over the course of the winter there. Whereas when we go back towards the summer, that regresses just a little bit southward, a little bit, there. But we see more storm tracks just along the North American coast, and again, they continue to go, just east of Greenland and then again into the Black Sea there. The southern hemisphere is a little more, I guess, homogeneous, like they're perfect circles almost, very symmetric, I guess is a better way to describe that, the storm tracks. So in the southern hemisphere, there's a lot of storm tracks that just circumvent the Antarctic continent there. And during the summertime, there's a lot less of those that occur there. So just in terms of where do we expect to see these storm tracks, again, they're in the high latitude oceans, generally speaking.
How are storm tracks defined in this case?
So I'm actually about to talk about that on my next slide here. So there's a number of ways that we can discuss that. So a lot of people have thought about it in terms of energy, in terms of minimum mean sea level pressure.
Eddy kinetic energy, or what kind of energy?
Eddy kinetic energy. That's the one I've seen the most commonly anyways. Yes?
So if you go back to that prior
Sure.
slide, I just want to make sure, are these both winter except it's just showing the strongest 5% on the right?
Yes, yeah, my apologies on that. Yes, so the strongest, I guess, mid-latitude cyclones are shown on the right, not
And
some of
this
the-
particular metric is what?
storm track density.
Yeah, and
So
how
how
is
many-
that measured?
This one is used specifically using mean sea level pressure
Okay.
and tracked, I think, using a Lagrangian technique that's
So
described.
the eddy kinetic energy looks different than this.
It can. I don't think they discussed that in this specific paper though, but it has been used as a metric.
Okay.
Yeah. Okay.
Because I've looked at eddy kinetic energy and I think it looks different than this.
Yeah, definitely. We will talk about vertically integrated kinetic energy a little bit later, which is slightly different. Yeah, please continue asking questions if you have them along the way. So again, I think a number of these studies conveniently use mean sea level pressure, again, because it's probably the most readily available in terms of data. Geopotential height is also a pretty popular one to use, just again, because you can plot that to a surface and then easily track that on a two-dimensional field. If figure out where these storm tracks are going. Are they strengthening? Are they weakening? And figure that out. But in order to better elucidate the contribution of mid-latitude cyclones, I guess, just in terms of their strength or getting a better feel for that, a lot of techniques have centered around either one-point correlation or the one that I'm going to talk about a lot here is spectral analysis. So taking a time series of data, decomposing it into time and frequency space, and pulling out the parts that are contributed to by cyclones that might occur on 2 to 8 day or so time scales. And I think a thing that's important to point out here too is that in the review that Ulbrich did here, the climatologies of storm tracks, regardless of the technique that you choose, tend to produce similar results just in terms of their qualitative, the result or the main thing, I guess, that they want you to take home with. Okay. So I guess some limitations that they discussed as well too is that even though yes, mean sea level pressure is generally a pretty good metric to figure out, how strong or how weak might a cyclone be, they tend to neglect the vertical extent of these cyclones just because the data is very large. You have to think about it in 3 dimensions now instead of 2, and it becomes a very computationally heavy task very quickly, and it's just a tough task to do, at least with the current frameworks, I guess, that we can use to make these type of analyses possible. Okay, so that's kind of where we're at in our understanding of that. So the next thing is cyclones and energy. So we take this energy, this imbalance, we convert it, I guess, into a potential internal kinetic and depending on where you're at, a latent energy as well. So I think probably the best example that I was able to find in what I thought would be good for this particular presentation is the Yin 2005 GRL study. So this one's been cited close to 1,000 times, mostly because this is one of the first studies, I guess, to show using the current ensemble of climate models that are used in the IPCC reports that in all cases where the climate models were coupled, the mid-latitude cyclones, these climatologies that they were able to compute for, I guess in this particular case, 1981 to 2010 versus like 2085 to 2100, they found a very consistent poleward shift in these storm track or mid-latitude cyclone locations. But in addition to that, because they actually looked at the vertical structure of these cyclones, they found that the baroclinic region, so in other words, an area where they can generate more convection and more energy, expands vertically upward, geometrically, at least speaking.
I don't know what that means, Andrew. Can you explain that a little bit better to me?
The
whole point 2.
So I have I guess a figure that's going to help me with this explanation.
Okay.
If that's okay. Yeah. So the reasons, I guess, for that, I guess, include a warmer upper troposphere and an increased tropopause. So the height of the tropopause is expected to be deeper, so there's more area than there was before, I guess, to convect new stuff along the storm front, I guess you could, if you want to think about it that way. Yeah, I have a figure on the next slide too that'll show this hopefully even better and maybe narrow down this explanation a little bit better. I guess a key point too here, again, we know that there's differences in the northern and southern hemisphere as well. So again, the southern hemisphere, especially south of about 50 or so degrees latitude, it's mostly ocean, so there's more region, I guess, for these storms just to continue going and going, and without land boundaries there, I guess, they postulated that they're able to continue, I guess, keep strengthening in this changing climate going forward. But in the northern hemisphere, this effect of them strengthening ends up actually being damped. Even though they're strengthening vertically, they end up weakening because there's so much energy being built up that inside the Arctic Circle that the pole to equator temperature gradient decreases a little bit, and therefore you would expect storms to weaken that way. So, yes, Luke.
I didn't know whether this is common knowledge or whatever. My first intuition would be upper troposphere tends to cool slightly.
Yeah.
I don't know what it is.
So it's, I guess, warming a little bit, I guess, because I guess there's more non-kinetic energy, so like latent and dry static energy that's available out there too. But because I think I'm going to have to pump that question too, because beyond that aspect, I'm not entirely sure, but I do know at least with the previous 2 points, the deeper troposphere is more responsible, I think, than the warming of the upper troposphere itself. Do you have
Yeah,
questions?
well, I think like this bullet point 1 and the bullet point 2 from the last, I think they're kind of different because there's the low-level response of that baroclinic zone,
Yes.
which is expected to be, but then the upper troposphere pole or equatorward of where
Yeah.
the jet is that's where the warming is, right?
Yeah, that is where the warming is, yeah, so, it's a little grainy, I apologize for this figure, but this is the best that I can pull it out here. So they have the December, January, February on the left, June, July, August on the right, and Northern Hemisphere is on the right side of these figures, and Southern Hemisphere is on the left. So the thing that immediately points out to me again is that this difference in eddy kinetic energy, which is used in this particular study, they find a really dramatic increase as evidenced by these, the red color bars here. So the mean that was computed for present day, so 1981 to 2010 or so, or 2005, excuse me, is these black contoured lines here. So you can see that the center of the this eddy kinetic energy maximum is both northward and higher in the atmosphere. So in terms of a net change, that's where, or what I mean, I guess, when they found that these storms are dramatically or getting stronger in the upper parts of the troposphere and also moving forward. But it's in the upper troposphere. I'm not entirely clear myself, I guess, what this translates to in terms of like how would that affect people at the surface? How much does that change precipitation, for example, too? But just, again, I think really interesting to look at it. That's why I'm including this here. But another thing, do you have a question? Oh, okay. So in the northern hemisphere, I guess during the winter time here, we do see, these storms do generally get pretty strong, I guess. I mean, not quite as strong as the southern hemisphere, even though it's the fall down there. But June, July, August, it's quite a bit weaker compared to its southern hemisphere counterpart, just in terms of, comparing it to the summertime anyways. But again, interesting stuff, I think, and why I think it's worth showing here. So it's a pretty key result and a very clean paper, I think, if people want to go back and read up on that. So now, we've talked about energy balance, we've talked about mid-latitude cyclones, and we've started introducing energetics, I guess, into this presentation here. So the main, I guess, data product, I guess, for this next part of the talk I'm going to focus on is the Aero 20C data product, which is ESMWF's new 20th century reanalysis product. So this one, per my reading of the documentation, is a little bit different from a traditional reanalysis in that it uses a fully coupled atmospheric general circulation model and also uses variational analysis to help constrain the model itself. So it assimilates surface pressure, marine winds, and then it's forced by observationally based analyses of sea surface temperature, sea ice, solar forcing, atmospheric composition, including clouds, aerosols. The references, I guess, given below there too. And the main reason, I guess, for using this particular new data set is that compared to, one, I'm slightly more familiar with the Aero products just in general compared to other products. So from a personal comfort standpoint, it was good to use, but in reading the documentation of why they created this relatively new product to begin with, they built this data set knowing that climate studies generally need to go back further in time, like where there are more observations available. So by including that and using modern variational techniques, which started being shown with COMPO 2006, for example, they showed that using a 100-year reanalysis product, they were able to actually create a data set, I guess, that's actually pretty feasible to use compared to existing data sets, assuming that modern data assimilation techniques are used inside this. So we implemented that inside the 20C. It's the first, I guess, product on it here from the new Air Climate Project, and there will be more projects, I guess, that are produced based on how studies, maybe including this one, show that, this is a good thing to use, I guess, for more climate studies here. So, very quickly, so let's pull some energy data out of the Air 20C data set. So this is one of probably the only data set I know that has energy variables that go back as far as 1901 or so. How good they're going to do, we're going to do some couple quick calculations just to assess the feasibility, I guess, of these variables. Are they in the ballpark of what we would expect them to be? But very first, I would be remiss to not give a quick refresher on what we mean when we say energy. So the total energy can be represented by E, which is the sum of potential, internal, latent, and kinetic energies here. Most of the energy is going to be stored as potential and internal energy. Latent energy is a small contribution, I guess, caused by water vapor processes, and kinetic energy being energy that's, I guess, generated like from available potential energy in the mid-latitudes mostly. So I just picked a random day here, one analysis of what, if you were just to plot these variables, because like frankly, like I didn't really know, how to envision this myself. So I think, it's kind of instructive to show what does total energy look like just on a per day basis. So,
Is it the surface?
so this is surface vertically integrated energy. So it takes, from the surface to the top of the atmosphere. It's saved as a joule per meter squared. So if you want to get the net energy the net energy at that particular location, or just across the globe, you would multiply that by the surface area for where it's saved at that grid point. And then if you sum that up across the globe, you can compute or figure out how much energy is in the Earth system at that point. So trying to slowly build up there to that. So I have redundant plots, I guess, on the top two. One is, the first one is total energy as it's directly saved in the data product, and the second one here is the sum of dry static, latent, and kinetic energy to get more or less the residual energy, which I have computed here as a subtraction of the two, just to make sure that, because I wasn't confident at the time, to make sure that the two variables were actually the same. So like if we use that equation to sum up energy, would they give you the same results? And based on this, it's about 3 orders of magnitude less in terms of error than the kinetic energy, which is, as we know, about 2% of the total energy as well. So from a residual standpoint, we feel good that summing up these energies or partitioning them into their individual components will be useful and with good efficacy. So I think I guess 2 things that stand out too. So I don't talk about latent energy for the rest of this talk here, but it's worth noting that you see the most latent energy, again, around the equator and the tropics. And then you see these, disappointing Greg's not here, but the plume structures here that go forward here. And you can see, generally that's a signal of mid-latitude cyclones again. This particular case, I think I pulled from May of 1983 or something like that, just a random spot. But the maximum kinetic energy in joules per square meter across the globe, you see about 4 or 5, I'd say about 5 or so, like obvious storm tracks associated with this vertically integrated kinetic energy. And maybe, I don't know, one, I guess it's obvious, maybe that's an atmospheric river that's off the west coast of the United States there, going into California, potentially. So if you look at that, and if you were to plot maybe 20 of these in a row, you would see that, it follows, I guess, what you would typically expect in atmospheric flow, or atmospheric flow, which is why I included that GIF at the beginning of this presentation, just showing that they move across the globe at 2 to 10 day timescales or so. So, doing a quick back of the envelope calculation, a recent study, well, before I get into that one, I guess. So backtracking just a little bit to Earth's energy balance. We know that, the energy has to be distributed in most places, but it's known, I guess, from Geckler 2016, they were able to estimate with pretty good confidence that 90% of all that excess heat, so that imbalance gets mostly stored in the ocean. So which is, again, 90% I guess is the key number there. Noting that sea surface temperatures have risen on average about 0.18 degrees Fahrenheit, or about 0.1 Celsius over the last century, and noting that, I guess, from this recent study too, that 2/3 of that warming has occurred in the top 700 meters, so meaning the other third goes down below 700 meters or so. You can do a quick back of the envelope calculation and find that, using the change in temperature, the heat capacity of liquid water and the density of seawater, multiplied by the volume, which is 70% times our surface area of the Earth times the depth of the ocean layer, which we have there, you get about 30 times 10 to the 22 joules of added heat energy in the entire Earth system here. So that's a good number to remember here. When we add ocean heat content and consider the other 10% of energy, so we take that same time period or what I've done here, I take the total energy, multiplied by the area at that given point, sum it up, and add it up for the entire 100-year period that overlaps with this same period. We get about 2.3 times 10 to the 22 total joules. When you take a ratio of that total energy to the ocean heat content, that's actually about 9.3%. So for just a very quick ballpark calculation here, this is actually a pretty good estimate here, which gives me a little bit of confidence that the Air 20C energy products are reasonably good to use for analysis, especially if we want to look at regional changes in total energy and further partition the role of mid-latitude cyclones out of this and how they've changed historically and in our future here. So let's break this down even further. So we've shown that this could be useful. How does this work, I guess, across the globe? Yeah,
So
you have a question.
Yeah, I know, I talked to you about this. Were you able to calculate what the energy imbalance at the top of Era 20C is?
No.
What is it for some of the other data sets?
Most of them I've seen are anywhere between, I guess, 0.4, 0.6, 0.7. The highest one I've seen was 0.71.
Those are estimates.
Yeah, those are
from their constraint.
estimates,
But I
yeah.
mean, if you just look at these top of atmosphere energy imbalances in a reanalysis data set, what sort of imbalance do you see?
I know they can be quite large, actually, and I believe, Mary, and I think you would probably know a little bit more about that than I do, like looking at, sorry to put you on the spot there.
No,
But-
I've only done polar energy balance.
Okay.
In particular. So.
Yeah, but I do know, I think the imbalance is generally a lot larger and a lot less, I guess, useful just in general from reanalysis products, other reanalysis products, at least as far as I know. Knowing that the 20C is a fully, I guess, coupled and, or a coupled model, like, I guess we're getting the, yeah.
That should have been some little simulation, but.
Yeah, but anyhow, so yeah, that's a good comment there. So just, yeah, that will be certainly something that, time permitting on my end, I hope to gain a better look at here.
So it's my understanding that the energy imbalances at the top of the atmosphere are very
Yes.
large in those. And so using a energy perspective where you look at the top of the atmosphere imbalance from a reanalysis product is not a good idea.
Yeah.
Which is why.
I haven't really touched that just for
Right.
that very reason,
Yeah.
honestly.
So this
Just trying to,
methodology looks like it would be a.
yeah. So I'm just trying to think of this more in terms of like how much energy was actually added, and let's just play with that a little bit. So digging a little bit even deeper. So these plots, I guess, that are coming up next, you should recognize too. So I wanted to break this down by decade. How has this changed by decade? So this also tells me not only, okay, one, what does it look like in each hemisphere, which I also have plotted up here, but two, knowing that the Era 20C works by assimilating observations that are available, where a lot of observations are available like more recently and before the 30s, and then again in the 50s, there's just really not a whole lot of data available. And I think, just going forward here, yeah, I'll start by explaining that too first. So we see, the first decade here, 1901 to 1910, where the reanalysis is just spun up, I guess you could say. It's hard to say, like, is that useful or confident? Yes, Matt?
Just a very general question. So this is a very interesting sounding data set. I'm imagining on what, April 1st, 2014. I'm sorry, 1914.
Sure.
1914. You look at a 500 millibar chart. It might not look exactly like what was really happening on that day. But yet, still, you feel that there's some confidence in assessing the general statistics of those things. And
Yeah.
would you like to say a little bit more about that?
The general statistics you mean, yeah. So I have I guess a few more, I guess, that I'm gonna show that might answer the rest of your question there, but, I guess I mean, you're not gonna know, I guess, exactly like, like, for example, like a geopotential height minimum occurred over one area and then it might have occurred like somewhere else. Like, I think a lot of, I guess in the background reading too that I did, like leading up to, I guess, these few slides here, a lot of them pointed out that on individual cases, I guess, so for example, trying to find individual storms like from like reanalysis data set, especially before the observational period becomes, I guess, more and more lush with results or available data.
So before the 1950s,
Yeah.
What would determine, say, T times squared and E times squared? Is it a known temperature gradient kind of regression?
I believe they
What do you think is the main control over the energy, kinetic energy, for example? Way
don't
back when.
quite know the answer to that question, but if you're asking about, I guess, how they spun it up, I do believe they started the model, I believe, in 1860, I believe, and they ran it for about 40 years until it got, I guess, again, yeah, I'm not,
I'm just naive about it, sounds
Yeah.
interesting.
yeah. Yeah, that's to the best of my knowledge, but I guess the short answer to that is that anything pretty much before like the 1950s decade, like, you have to take, it's cool to look at, but not necessarily totally, I guess, useful in terms of, if you're trying to look at individual cases too. Yes,
So
yeah.
I know the 20th century analysis that Gil Campo did, he used just sea level pressure.
Mhm.
Right? As far as I know, there was no other observations. Anyone? Is that the same with?
Yeah.
They just use sea level pressure?
It's
on this as
sea
well?
level pressure and marine winds, I believe, are the only two that are consistently assimilated even back into like the 1900 first decade.
Okay.
Yeah, and then as they introduce more, I know the 1930s, I think they started getting more sea level pressure data available, especially after the war, and then in the 50s, we kind of discussed that yesterday too, with radiosonde data and why.
But I don't think they use radiosonde. They don't use radiosonde data.
Not, well, I think they make analyses from that and then force the model, I guess, to use that to
I don't-
train.
Not for Gil Campo's.
Oh, no, sorry,
I'm not sure
I'm
about
talking
this
for
one.
20C, I apologize.
But also, wasn't, they're going around this something before 1950.
Yes.
Do you have any idea why there's such a steep rise in the early part of the 20th century?
That early on, I could take guesses, I guess, but not entirely confident, I guess, like why that would necessarily be the case on without knowing like how, like looking back at weather extremes, for example, and, was that a cold period, I guess, in our climate, for example, too, or a warmer period where in all three hemispheres where you see like the total energy like actually positive in multiple cases. But yeah, I guess what this is actually implying then too, if you break it down by decade, is that the southern hemisphere starting in the 1910s, I guess, has consistently lost energy relative to periods before that, but the net energy gains by the Earth's atmosphere has been gradually increasing, but especially since the 60s or so, when
So this is basically temperature we're seeing, right?
more or less, yeah, because it's almost entirely dominated
The
by
relative humidity doesn't vary too much.
Not
So
too much,
yeah.
Yeah, to the best that I can interpret that. So yeah, we look at this one, and I guess the next one I have available too is the kinetic energy. So again, something that's kind of interesting to look at. So we built this up, I guess, discussing that the temperature gradient from the pole to, or from the equator to the North Pole has decreased quite a bit, just in terms of total energy. So would you expect there to be a total decrease in kinetic energy just in the entire northern hemisphere? And that's actually kind of what's seen here in this particular data set here. The vertically integrated kinetic energy by decade has been decreasing pretty consistently, I guess, in the northern hemisphere. Not necessarily for mid-latitude cyclones, but just across the hemisphere. So, but it has been increasing in the southern hemisphere so far, and that's again results by the UW-AOS study that kind of suggested that, but especially like in the upper part of the troposphere where kinetic energy, I guess, is integrated from that part up, and there's been a lot added there. That's probably the main contributions there, at least in the southern hemisphere, and why you see that. Yes, Michael?
Could you, you mentioned earlier the spectral analysis, could you actually explicitly take the data that you have and do a decomposition on 2 to 8 days or whatever, and look at this kinetic energy and those presumably baroclinic waves and see how that's trending relative to other?
Absolutely, yeah. And we're going to use that for a slightly different product. Yeah, so that's oncoming. And I have some results. I didn't include them in this talk, but they're available, I guess, as well, too. Those are ones that I did more for a class project, but elected to disclude just for keeping this discussion going here. So, but yes, we do. And I do walk through an example of that because I wanted to. Okay. And then, I guess lastly, before I move on to the spectral analysis part of this talk here, so this is the same variable as the last slide here, kinetic energy, but broken down only from 30 to 60 degrees. So we're more likely to see mid-latitude cyclones, and also mid-latitude cyclones, I guess, thinking in a general circulation sense. We know the kinetic energy, I guess, in the mid-latitude hemispheres. I guess there are stationary waves, transient waves, and the mean state, I guess. And most of the energy is like maintained in the mean state and the transient wave. So if there's a net increase or decrease, it's probably going to be about 50-50 or so, I think, between these two. So just from the qualitative, but not necessarily for sure method of using this to evaluate that, we can see that in the southern hemisphere, you could probably deduce that the total kinetic energy that's included in these mid-latitude cyclones is, again, increasing by about 2 times 10 to the 16 or so joules per decade, roughly speaking. But in the northern hemisphere, that's slightly negative, what we've seen before, but again, closer to 0. So that implies, if we look back at the last plot here, where it's been relatively decreasing with the exception of the 70s or so, that most of the decrease in kinetic energy is actually occurring either in the Arctic or near the equator. At least that would be my first guess on that. So hopefully I've whetted the appetite here a little bit, just in terms of thinking about energy cyclones and radiation balances here. So we're going to jump on to spectral analysis now. So how to get an even better, clear look, I guess, of what mid-latitude cyclones might look like in our data sets. This is probably the single best resource I've probably seen, just in terms of explaining it to me, where I spent most of my time looking at radar data and whatnot, and being able to read this paper, kind of understand the math, but mostly understand the technique and the software that's provided with it. I think this is an extremely powerful tool, and I think one where, by showing an example or two, like, we can collectively use this to deduce the role of, or continue investigating time series of interest here. But in this particular case, because we're interested in cyclones, I wanted to come up with a illustrative example here. What do we mean by spectral analysis, and how do we actually see them, and how can we plot it, I guess, for example. So let's take an arbitrary point anywhere. Let's say here in Madison, at the top here, I made basically as mean sea level pressure change that very sinusoidally across obvious 6-day intervals here. And I have 60 days here just for, again, totally arbitrary or so, but the amplitude, I guess, of these changes is about 5 hectopascals, so per amplitude, so a net change of 10 hectopascals. So like one day it might be, let's say, 1,005 hectopascals, and then a couple of days later it's 995 hectopascals. If we run the software, I guess, on this, we decompose this spectrally into, like, okay, we clearly see that it's a 6-day cycle here. You would expect, using this technique, that the main power, I guess, so the square of the amplitude, I guess, to occur at these 6-day cycles here. So there's a lot of stuff here, I guess, that you could think about here. So one is, you want to break it down into using, well, by way of Latude, I guess you could think of it too as a fast Fourier technique. Where you take something in real space and you think of it in terms of a wave. And one thing, I guess, that becomes important to think about too is that instead of it being like a, point A to point B time series, you have to think of the time series as circular. So if, like, the series is coming around sinusoidally, in this example, it kind of works just because, connects at the dot, or connects at the beginning or the end. But if you want to do a real-time series, for example, like, let's say, mean sea level pressure, like, in real time, but actually varies, quite a bit from one decade to the next. If you connect the ends there, you're going to come up with a result that's pretty dubious, especially at the beginning and the end. So a important thing, I guess, to do here, and why you see this black line here, the black line is this cone of confidence or so. So that's computed from the variance, I guess, just across a given time window here, and normalized, I guess, or they normalize the power spectrum according to this variance here. So you get anything from, I guess, day 10 to about day 50 or so. Anything that shows up as a 6-day wave pattern here is actually usable here. So, and again, this is integrated and shown as a green line, I guess, across this plot here. So anything that shows up, roughly 6 days here, again, that's what we wanted. That's how we get it here. But you might be asking yourself here too, like why do we see significant power like 4.5 days and maybe 7.5 days too? So whenever you're taking the time series, you have to assume a shape in a wavelet analysis. And in the torrents and compo method, the main one to use is a traditional wavelet. So it looks more or less like a damp sonogram of sorts. So like there's a peak wavelength in the middle that dampens out and gradually becomes zero at the end. So the shape of that, when it's fit to the time series, actually expands the middle of that a little bit, and you get some excess power that occurs, on days that are immediately preceding and or ahead of that time as well too. So the next, I guess, couple slides here, I guess, will show you just how easy, I guess, well, there's only a couple lines, I guess, that you really have to play with in this particular software here. So like, let's say I want to add a sinusoidal wave that, varies by like 1.5 hectopascals and occurs at 2 days. You can see it superimposed very briefly here. You get a power spectrum that occurs right at 2 days here, but we know that it's not statistically significant based on the variance. So like we want to know, like, is this an actual signal or is this just background noise? Again, I kind of have to speed through this just a little bit. If we have more questions, I guess, about the specific technique, I'd be willing to talk after the fact here. But so if we take that same 2-day variability, we make the amplitude of those waves, let's say 4 hectopascals instead of 1.5. Now you actually get a statistically significant signal, and because it has a lower period, you can be more confident at the edges of the time series that you're getting more statistically significant data to use. So in terms of wanting to evaluate the role of mid-latitude cyclones and thinking of them as 2 to 8 day features that are embedded within time series, you can take the amplitude that's measured here within this period here, take a mean or take the maximum amplitude, for example, which is fairly common practice, record that at your time series, and then you can do a trend analysis based on that. So,
I'm sorry, the spread that you did when you constructed time series at the beginning and end.
yes.
So one thing in conventional time series is just the tape at the ends of the time series, and then you get that problem. Is that the low that diagram is being a filter?
Yeah, that's the variance in which the power spectrum is normalized to. So like that's just, I think the window is about like a couple days or so. So it's taking all the variance that's saved within there. So even though like the maximum, I guess, like from end to end is 5, when you, I guess, count 2 waves or so, like that's why the variance would be closer to like 17 or 18 hectopascals as opposed to just 5. So it kind of answers your question. Yeah, I'm at 40 minutes or so, so I'm gonna wrap this up here in the next 5 slides or so. So yeah, wrapping up here, I guess, with these 2 here. So I promised some CMIP data here to include. So I have 2 products, I guess, from the NOAA GFDL. We're going to take mean sea level pressure data from this particular model. We're going to run it, but we're going to use or assume that they're 4 to 10 day variable. And we use 4 to 10 day instead of 2 to 8 because these data are provided daily as opposed to 6 hourly, which is what this Era 20C is available in. So we have to backtrack a little bit, make it a little bit less comparable to previous studies, but to actually make this somewhat useful and comparable, or just to illustrate here, I think we need to do that. So yeah, the techniques measured there, you guys can ask me about this on the next slide. So if we take every point, I guess, in this data set for this specific historical model run here, we can filter out the variability, and we can find, using this example here, some pretty interesting changes across the globe, a lot of regional changes in sea level pressure.
I'm sorry, you just go back one.
Sure.
So I mean, the wavelet is showing you the energy over a particular time period at a particular frequency.
Yes.
Is it positive definite?
I'm not sure what you're at. Are you thinking in a statistic?
No, I'm trying to interpret the next plot is, is this the change in mean sea level pressure or the change in variance of mean sea level pressure?
This is the change in I would interpret this as variance in mean sea level pressure, just because it's taken across the 4 to 10 day period or so. Well, not necessarily variance, it's using the technique that I just outlined, the wavelet technique. So it's pulling out the signal that's caused by that. So in this particular case, yeah, I probably should have included an example to show like what that is, I guess, like from a representative year, which I do have. But yeah, these changes, I guess, could be anywhere between like 30 to 60 or so hectopascals occurring in 4 to 10 days or so. A lot of them occur on timescales less than 4 days, and there's a lot of variability even north of, I guess, even 20 or 30 days or so too. But again, you can use that with that time series, I guess, too. But
Yeah, it's hectopascal, not hectopascal squared.
this is hectopascals, yeah. So this is amplitude. Yeah. So not the power spectrum, I guess, too. So we want to know, like, okay, my question was, have these cyclones increased in strength or decreased in strength? So these are two, I guess, different versions of the same model that I'm going to compare here. We can talk about why this way maybe or so. Yeah, the documentation wasn't entirely clear to me, like how the coupling is different between the land and the ocean, for example. But still, again, this is the same data that a lot of people are using now to look at. And I think using this, I think we can get a global view of how cyclones are changing. And the first thing that points out to me, I'll focus on the northern hemisphere so we can finish up here in a few. There's a net decrease, just off the Iberian Peninsula here, so the eastern part of the north.
Decrease of what?
Mean sea level pressure associated with mid-latitude cyclones.
Okay.
So there's the black contour that's about out to 1 hectopascal. It goes down to, I believe the maximum here is about -1.8 to 1.9.
So that means they're more intense then?
No.
The amplitude has decreased. This is an amplitude.
So I don't know that you can actually say that, because the wavelet, so as Anker pointed out, wavelets can have both amplitude, or can have positive and negative amplitude, depending on the phasing of your particular storm.
Yeah.
I got to look at your method closer, and to me it just looked like you just did a high and low pass filter, basically.
Yeah, more of a high pass. Yeah.
So what you're looking at is the delta H Pascal. I don't know how you did the trend here, but
Yeah.
Yeah.
So compute that across the 105-year period.
But what is your data set that is it sea level pressure or
It's mean sea level pressure.
It's filtered sea level pressure?
Yes.
So this is a trend in,
Filtered sea level pressure.
but it's not amplitude of storms, right? I mean, if you took the wavelet, and you squared that, then you would have something that is indicative of the amplitude of storms. Or if you just,
So what you're saying is I should stick with the power spectrum and not
well, you do either one, but if you did a trend in the power spectrum, then you could look at changes in amplitude. You see what I mean?
That's, sort of what I did. I square rooted it before making these trends. So amplitude. So you're saying use the square of that.
No, I'm saying if you applied a filter to sea level pressure, and then you do a trend, but I don't know how you interpret
That. I just want to know the variability in 2 to 8 day or 4 to 10 day cyclones.
Right, but when you say variability, you either mean variation or variance, and it's important the difference there, because the variance is what you care about.
Yes. So yeah. So I guess for example, where it says -1, if we imagine, high pressure, low pressure, it's decreased by 1 or 2 hectopascals over that 100-year period.
But I think Dan is saying that's not what you described on the previous slide that you did.
Yeah.
Isn't actually measuring that. I think that's what he's saying, right?
I just don't know I don't know how to interpret this anymore.
Yeah. Yeah, I'd say we'll take this offline, I guess.
That's okay.
Yeah. So I had two, I guess. I mean, yeah, the point is, I guess the two models showed stuff that was different. This trend is a little bit different. What that actually is, we'll clean it up a little bit, and I'll finish by summarizing. This whole thing is pretty complicated, so kind of what we just discussed here, as you can tell. There's a lot of good techniques. Hopefully, the wavelet analysis, I guess, is the one that's most obvious to me, how you can elucidate variability from mid-latitude cyclones that way. The 20C product, I think, will be really good for looking at this. It also has mean sea level pressure data available. I think that would probably be the next obvious thing to do in looking at these trends, and especially with the energy data also being available. And in the small, I guess, subset here too, there's a lot of, I guess, change that varies between these, and it's definitely worth looking into. So, thank you, everybody. Hope you enjoyed, and I will take more questions. Yes.
So I think it's a great idea to use to look at energy and raw energy and something like the 20th century analysis, because you have ideally you have a consistent set of inputs into something like that, and so you don't get these huge climatic changes that come from different observing platforms.
Yes.
It'd be really interesting to know what data goes into that, and you know, and get a sense for how robust or how consistent that is. But I think is a great approach.
I appreciate it. Thank you. Anybody else?
Do you think about looking at available potential energy at all, right? Because you
thought
looked
about
at
it.
total energy, but really what matters is the available
Yeah, what's
potential energy.
available. Yeah, so
But
that's
it's more complicated to calculate.
It's extremely complicated to calculate. It's one of the, I looked at that probably, I want to say 3 or 4 weeks ago and start coding in them, and it's a mess. I mean, it's doable, but I'll probably have to
There's
do
got to
that.
be some codes written for that.
Probably, yes. I mean, people have looked at it, but I haven't found anything that was very recent on that specific topic, but mostly because, yeah, it's a tough thing to use. That would be really cool to see, is there more available potential energy for these cyclones to use, I guess, whenever they're developing. And I think that would be really cool if someone can figure out a clean way to do that.
I think Paul Gorman has worked on this recently.
Okay.
So, using a moist version of available potential energy. That
Okay.
would be something to take a look at.
I think the initial Lorenz papers, I think, discussed dry energy
Yeah,
mostly. Yeah.
that's right, yeah. So if you want to look at it in the real world, you have to think about moisture as well.
Sure. Oh, of course, yeah.
Yeah.
Moisture's also interesting too, but
So hence the more recent work.
sure. Great, thank you. All right, well, thank you.
All right, thanks.